daemon, audio daemon. It seems to be working now.
Okay, very good. Okay, so we're happy to have Upamanyu Moitra from ICTP visiting, and he's going to tell us about interesting aspects of near-extremal black holes.
Thank you very much. I would like to begin by thanking the organizers of the seminar for giving me the opportunity to speak here. It's been very nice. So the topic that I'm going to talk about is nearly extremal black holes and some interesting aspects of physics that we can learn from studying the universal nature of near-extremal black holes, which is the ADS2 geometry. So this is the near horizon ADS2 geometry of near extremal black holes, and it arises universally in all extremal near extremal black holes, and some of the relevant work in this regard are by Harvey and others. So this is obviously a periodic diagram of the ADS2 black hole. And I'm going to tell you what sort of interesting physics we can learn just by studying the near horizon region and the associated near ADS2 geometry. So because I am in a place which developed some of the central ideas behind what I'm going to discuss, I have made particular choice of the topics that I'm going to talk about. So one thing I'm going to talk about is fluid dynamics, which thanks to someone in the audience, we know that is intimately related to gravity via ICTP correspondence. And I'm also talking about something which is completely disparate, which is the strong cosmic synthetic conjecture, which I'll simply refer to as SCC in the instant discussion. I'll first try and discuss fluid dynamics, and I'll see how far I go. So the basic strategy of today would be to discuss simply solving the wave equation in some near-extremal background, and we'll see that we will end up learning a lot about interesting physics by studying this equation. So the work on fluid dynamics was done in collaboration with my advisor Sandeep Trivedi and Sunil Sake, who was the graduate team. And second work which I did myself was on strong cosmic synthetic conjecture, and there was some unpublished work which was also part of my team. And there's also some work in progress, but I don't think I'll have time to go into them. So without further ado, let me quickly summarize what we know about fluid gravity correspondence. And fluid gravity correspondence was obviously the relation of fluid and gravity is not new, and it's been known for a long time since beginning. I would say with the work of Rachenbury, then with the work of Theodore, then in the context of ADS2 by Thorne, Karinex, and others with the context of linear gravity, and then finally in 2007 and Randomly discovered what's now fluid gravity correspondence, which is nothing but a consequence of the ADS. So let's take the simplest data. Let's take the ADS first black hole and write the metric in this patch in the Eddington-Finkelstein coordinate. So the static metric looks something like. So this is the blackening factor, which I'm writing as a party for the also black gradient. So all my discussion today will concern 4-dimensional black hole, and in some units, this will be Q over RQ. This blackening factor. T is some crystal temperature of the black hole. In individual coordinates, the symmetry looks like this. So this is of the black hole. This is the black gradient where this dx square, this is the topology of R2 and not H2, as is the case for spherical symmetry black hole. So this is our starting configuration. And now to discuss fluid gravity, we simply we can write the boosted black hole by making the following item. We can write this time-like coordinate TB in terms of mu ds mu, where mu is 0, 1, 2, and this mu is a free vector, and the dx square we can write in terms of the. So this mu is nothing but the for example, in this particular case, this mu is the free velocity of a fluid at rest. But we want to now boost it, and this dx square can now be written as mu dx square, right? X mu as this is d, and x coordinate. This new coordinate is on the boundary, sphere, where this mu is the projection tensor defined by w mu plus u mu q. And for any arbitrary, and this u square has a normalization condition that for time-like observers, u square obviously versus square to -1. This is the 4D solution. This is the 4D solution. Yes. So x mu, okay, yeah. So I should probably write it as x mu coordinate is the boundary coordinate. This involves the b, the time-like coordinate, and this x is just like the dx and y. So this dx is. So these are 3-dimensional boundary coordinates, and all the fluid, of course, is supposed to be on the boundary theory, and we now make a boost in the fluid frame in the 3D substrate. We make a boost. So this is what's characterizing the boost. Generally, u mu, that which velocity, the projection tensor associated with this fluid velocity, and this means obviously square to -1. The time-like of the verb. So now this is so far completely expected in the sense that these boosted solutions are also solutions of the 4D Einstein equations in the presence of a negative orthogonal constant in ADS4. But now we want to study fluid dynamics in the long wavelength approximation, in the sense that this is the starting solution, and we want now instead of this being constant functions, for example, this temperature T is the constant, this mu is the constant. We now want to make this temperature and the chemical, and the free velocity slowly varying function of the boundary coordinates. So this is the long wavelength approximation. So this is a starting configuration, but now we want to study it in a derivative expansion. And how slowly? So for example, in this case, let's say del T over T, we take to be, so if omega, so So this del generally denotes the spatial or temporal rates of variation. So the fractional rates of variation are simply the spatial momentum for the linear variation, spatial momentum of movement. So, but right, this is omega or n del two, and this should be much less than temperature itself. So the fluid should be varying, the spatial and temporal rates of variation should be much smaller in units of the temperature, because that's the only scale available here on the boundary theory. On the on the bulk, obviously we have the APS scale, but that's immaterial. On the boundary, the only dimensional scale that appears is temperature. And now what do we do? So now we write this is S0 square. So we write the new line element as B S0 square. Now varying as a function of the boundary space-time coordinates x mu. But for a generic profile, let's say T mu or U mu, this will obviously not satisfy the Einstein equation. So to satisfy the Einstein equation, we have to add to it some terms. So some correction terms. So what we have the correspondence developed by this proposal is that we add this term order by order in an expansion in let's say omega over t or t over t, which we generally call epsilon, which is the perturbative parameter. So this is an epsilon expansion. So we feed this into here and we get some as yet unknown functions, and we get some differential equations from the Einstein equation. So for example, if the differential equation is generically of this form. Mn corresponds to the bulk electric fluctuations. So this is the first order correction that appears, and then there are some source terms which arise because we have varied this part. We have made them a generic function of x. So order by order in perturbation theory, we can solve Einstein equation and get the solution. And from a certain sector of the solution, which are sort of the constant equations in the Hamilton-Jacobi formalism, when we write them in terms of the boundary variables, we simply get the Navier-Stokes equation. So the bulk Einstein equations correspond to fluid dynamics Navier-Stokes equation on the boundary. And given any nice conformal fluid on the boundary, and they had also developed with so I should say plus maybe and so it was obviously generalized to more general settings. So this question? No. These are solved exactly in R. These are solved just perturbatively in epsilon. In this spatial and temporal, this is gradient expansion. So these equations are solved exactly in R. And so that's a good point. So one of the main issues that I'll encounter is that I have to solve them everywhere in R, not only near the boundary, but I have to make sure that. So the statement is that any boundary fluid dynamics utilizes to something nice in the bulk. So in particular, the bulk perturbation theory, in terms of this epsilon, they should also be well defined. Actually, at least up to the black hole horizon.
I think that was these are just in EDS.
Yes.
If you're using like a grand type extension, you put some perturbation on the boundary,
yes,
and try to integrate in. It's usually very hard to actually integrate in when you have an actual solution. Not an acid product.
So in this case, that's the remarkable utility of one more. So this derivative equation, so this differential operator, because of the derivative expansion, because of the way the perturbation theory is organized, this differential operator happens to be an ordinary differential operator in R. So it's not a partial differential equation that you are tasked with solving. You are solving an ordinary differential equation in the usual fluid gravity setup, and then you can impose, let's say, you put normalizable boundary conditions at infinity. You put some finiteness condition near the black hole horizon, and it's an ultra most of the time this is an ultra local equation, and this whole expansion was let's say Q by Q. So they have a Q-wide construction. So you solve it here, and you can just integrate in for every point which I have called x mu. So at every point x mu, we have got a unique solution. Yeah, so this is a differential operator, and the form of the differential operator, because of the nature of the perturbation theory, remains the same in each order in the perturbative expansion. And in particular, I'll be studying one particular very simple operator, which is just del psi equals 0, and I'll explain this is not simply a toy model. This will be important, for example, in the spin to excitations of the gravitational mode, which are tensor excitations. But I won't go into the full details of the gravitational electromagnetic perturbations today, because they're sort of they're technically complicated, and the main idea will be clear just from studying the massless planar nature. So this regime that omega or k should be much smaller than t, this is obviously the usual fluid dynamics where the derivative expansion holds. But in the recent years, motivated by studies of the ICTP model and various aspects of JT gravity, which I have studied also during my PhD, we were motivated to think of the following question as to what happens when this omega or k, the spatial and temporal rates of variation of the various fluid parameters, they are no longer the smallest scale Simpson problem. In other words, what happens when we take temperature to be much smaller? So admittedly, this is not fluid dynamics in the way that we understand it, because fluid dynamics, of course, and you would say that this, by its very definition, is outside the realm of fluid dynamics. So I would agree, and I would say, okay, let's see what happens when we are in this. But of course, when we have only temperature in the game, this is not something we can do. So we would also need a chemical potential, another scale in the problem. And obviously, because this is motivated by a study of near-extremal black holes, we need that near-extremal black holes need to have some sort of charge to have a definition of extremality. Because simply with temperature, you would have a short shell black hole. But if you want a near-extremal black hole, you would need something like a right knot to black hole or black vein, for which you need a temperature. And in this case, the pertinent geometry, at least starting geometry, is F RT mu. This way, and then the same thing that I have written earlier. And in 4D for good measure, the RT mu is given by and this Q and M are functions of P and mu, which is very straightforward to work out. Now, in this case, FRT, so because there are competing factors. There are different parameters here. There are competing factors. And okay, let me draw this file and draw the. So this is I'm drawing a near-extremal Wagner knot from. This is the outer horizon. This is the inner horizon or Cauchy horizon, and this, and we would like to. So this is the non-extremal iron black hole. The interesting thing about Wagner from black brain is that this F factor, this can be 0. Even for short it can be 0. But what's interesting about it is that it can have a double 0. So for the particular parameters, let's say when we take GM to be, so RH, so the black hole horizon is that R equals RH, the outer horizon. So this will be my notation for the rest of the talk, or rather the extremal location of the extremal horizon is that R equals RH, and when Q is square root RH square, this F becomes R minus RH square times something over R to the 4. So as opposed to the Schwarzschild black brain, in this case we have a double 0 here at R equals RH for the exactly extremal black hole. And near the horizon, the geometry assumes the following simple form. This part of the geometry is ADS2 written in coordinates. And this part now, because of the attractor mechanism, essentially, this near extremal horizon, this R square becomes RH square. So the near the horizon, the geometry factorizes into the ADS2 part and the R2 part. And this happens, so this is what I was referring to in the beginning of the talk, that this happens universally for extremal or nearly extremal systems, that no matter how many dimensions there are after, it always happens into, whenever there's a double zero, we always happen into an ADS2 time some compact state. For example, for even for asymptotically Minkowskian black holes, right now some black hole, this would be ADS2 times F. And this, so this is that T equals 0 for T non-zero 2 for the temperature much smaller than the chemical potential. And let me write the fixed chemical potential that I'm studying is so okay. I have put ADS to 1 everywhere, and the chemical potential is given just by the horizon radius in at extremality. And what I will be doing is that I will keep the chemical potential fixed, but I will raise the temperature as we go slightly away from extremality, and near extremal is defined with condition that is much smaller than mu. Oh, so here, so GM and Q, you can write them explicitly in terms of mu and P are equivalent to RH and P, and when you take P to 0, or in other words, simply the surface gravity of this F, you can write it, you will find that it's proportional to R minus RH. Sorry, surface gravity is evaluated at R equals RH, and because it's a double zero, the first derivative is also 0. So in terms of let's say when you have a Schwarzschild blackening factor, when you take the first derivative, that's non-zero, that gives you the Hawking temperature, for example, of this blackening factor at evaluated at different horizon. So in this case, because it's double zero, this gives you zero. In the sense that the other input acts otherwise. And so this is the t equals 0 case, and the t equals non-zero is just as simple. It's also an ADS to. So I am using some rescale t coordinates for convenience here, and the rest is the same. So this also remains ADS to when you perturb it slightly away from externality. Okay, so let me do the simple thing that I promised. Which is solve the massless Klein quantum equation as a prototype for the fluid gravity. So let's study this equation. And this phi, let me write in terms, obviously, I think the videos the other part anyway. So I want to write it as a perturbation. So this is our answer for solving it. So note that because the matrix has is invading under transformations of b and x, this immediately means that we can write in terms of plane wave modes like this. And to zero order, what are we doing? So we have this boundary. What we are doing here is turning on as a sort of impulse some time varying source like this. So this is, we are turning on a non-normalizable mode on the boundary. This is a constant non-normalizable mode. So not completely a constant, but this has the following dependence on the spatial and temporal coordinate. And we want to study the response. Namely, when we study when we turn on this phi 0, we want to know what happens at higher orders when we try to solve this equation. Namely, what is phi 1, phi 2, and so on. And the equation is quite simple. When we want to study phi, so this indices, they correspond to the order of perturbation theory in epsilon. And epsilon in this particular case would be omega over mu or t over mu, and they are of the same order. So here we will show perturbation, we will try to organize the perturbation theory in terms of this epsilon. So let me first write down the equation. And then we will neglect some terms. So I won't give this particular distribution important. Okay, so this k squared over here is already order epsilon square. So let me just get rid of them right away. So this phi 0 is order epsilon 0. This phi 1 is by various order epsilon 1. So this is order epsilon, and omega by itself is order epsilon. So this product is of order epsilon square. So in the perturbation theory, we can neglect this term. So this is what happens in the traditional fluid gravity performance. So we are left with solving the following equation. And this differential equation is very simple. And I can write down solution right away. So this is y, let's say this is b minus. So I'm putting the lower limit as r infinity e oh. Very right. The most important thing. So the 1/n term is there. It comes from just integrating this inside near-extremal. Oh, sorry, this is part of the outer integral. I'm sorry. Because when I integrate it once, I get this part. So this is some arbitrary constant which is correlated with A. A and B are constant here. If I write down the 4, so this is the ABS to 4 region. This is the backward parameter R equals RH. Let's say I am in some fictitious boundary here, and this asymptotic boundary is at R equals infinity. So this is a form of phi 1. So let me show you what happens for large and larger and small r in the near the backward horizon. For large r and r goes to infinity, it goes like it has the constant b times minus something 1/r plus a minus something else r. So because we want to impose normalizable boundary conditions for the solution at infinity, we can set this b, which is the constant, to 0. This b goes away. But even after setting this b to 0, when we try to expand this solution near RH, we get the following behavior. So this is a minus RH. So RB is the fictitious boundary, RH is the horizon. R minus RH. So in an expansion near the horizon, these are two different kinds of singular terms. One goes like 1/r minus RH as one approaches the horizon, and another is dog. So in the fluid gravity correspondence, we want the perturbation theory to be well defined everywhere from the horizon out to infinity. So what we do, we remove this divergence by a choice of this constant A by just setting A to this one here. Okay, we can do that. We do that. But then when we do that, we end up with the following result, that this coefficient, which is log of r minus RH over RH, that does not vanish. When we set this to 0, this does not vanish. And therefore we get some divergent term, which, I mean, after having set this to 0, And besides some regular terms which we don't care about. So apparently the fluid gravity correspondence breaks down when we try to discuss extremal black hole. And this is one of the reasons in the early literature of gravity correspondence that people did indeed try to think about this question of what happens when one takes the extremal limit, and I mean, then the question that is say that it is breakdown because of this double zero and when the two horizons are coming together, the inner horizon and outer horizon. Apparently, this breakdown.
Why are you choosing such a first term?
Because this is the more singular one, so we want to set the most term to zero first, and then whatever we left, and we try to set this zero, we will still have some divergence. I mean, there's no way to get rid of the divergence by a choice of the form. Yes, yeah, yeah. For example, when what happens in so it all happens because this factor a part is of the form 1 over r minus r x square, and this 1 over r minus r x square gives I mean, if we just try to extend after integration, we give r minus r x and a log. So because the double zero, but if we had a single zero, that would simply be 1 over r minus r x. We would not have such a term anyway, and there would be just one log, and we would get by just by choosing this particular constant. But even for in this particular range that I am interested in, even that would not be good enough because the perturbation theory, I mean, all the things would be finite, perturbation theory would seem to work. So, why are we even studying this problem? So now what I'm going to tell you is that our confusion of such a divergence is premature, and when we try to think more carefully, the divergence will not be there. The reason is the following. The reason we have to what I said in the beginning, the interesting role played by the ADS2 region. So, did I write the meat for it? I have written down the following metric for the near horizon region, which is ADS2 times R2. But in going before concluding that, we have to examine an interesting property of this metric, which is that the ADS2 region is very special in the sense that among the boundary coordinates, the time-like direction plays a more special role than the spatial direction. In other words, in the deep infrared, as one goes to the black hole, near the approaching the black hole horizon, there's an emergent symmetry of this geometry. And the symmetry is as follows. And this symmetry is possible only because of this factorization. The symmetry is that line element of that near horizon metric remains invariant under this r minus rh goes to rh going to lambda p. So when the scale oppositely, when if r and b scale oppositely, the line element remains invariant, as you can clearly see from here. And it's because of this reason that once we are sufficiently close to the horizon, this finite frequency term, we cannot really neglect it. In other words, sufficiently close to the horizon. So I had earlier sort of cavalierly said, okay, we can drop this term because both by epsilon squared. But in the near horizon region, this frequency dependent omega enters in different. And one of the ways it enters is here, where omega is closely associated with this symmetry. And if if you try to do the analysis, the near horizon analysis carefully, you will find that for a okay, yeah, use this part. That's sufficiently close to the near horizon region. I'm taking my R star to be here over. And this following statement is true only near the horizon. That so now in this coordinate, RH, R goes to RH is R star goes to minus infinity, and you have the black horizon, the usual reticular torus coordinate. So I've just written that equation in the near horizon region in this form, and this shows you why we cannot neglect this term, because any here because of the symmetry that I was discussing earlier, V goes to lambda V is omega goes to 1 over lambda omega. So this omega and this R star are inextricably linked. Sufficiently close to the horizon is inconsistent to drop this term. Therefore, we have to and when we are discussing the near-extremal black hole and the near horizon region, what we have to give up on this is on the algebraic nature of the differential equation. And now we are forced to deal with this differential. And this differential equation too is easy to solve. I will not try to solve it in real time, but instead just give some.
You drop the keys for the terms because the scale of that is not.
Yeah, that's a great question. So this kx square doesn't scale like that because kx square they are associated with the x direction, with the remaining direction. So this direction, this does not participate in the algebraic definition.
Okay, this R minus R each is
Exactly. Exactly. So R minus R H scales is so it's associated with time direction. Here the time direction is more special than the other direction, and which is why frequency plays a more special role. So and so what I've written is always really small, and this hides all the elements. So an exact solution for this differential equation involves these two parts, which has this integral form. The intermediate part is associated with an exponential integral function. It is a special function which is dealt very carefully in, for example, Abramovich-Stephen. But this exponential integral function makes all the difference in the world. So now, when we take R star to infinity, it turns out from the properties of the exponential integral. Okay, one more thing. Because we want to impose infinite boundary conditions on the horizon, which is really necessary for fluid dynamics, we can get rid of this term. So this does not an outgoing rate, so we can get rid of this term. This is an immediate constant which does no harm. So the remaining part, it turns out that as r star goes to infinity, this term drops away. So the solution is completely finite towards the horizon. But you will now tell me, oh wait, you were discussing the log before. Weren't you discussing something like this log solving the outside equation? Getting it. So now what we are essentially doing is some math asymptotic expansion. What we'll essentially do, we'll solve this ultra-local equation in this region which is outside of ADS2. And in ADS2 region, we will have to solve for the exact equation, and we have to match them at near this fictitious boundary where both the descriptions remain valid, and from there we can carry out outward the integral and get what we get. So now this log term, this emerges rather curiously. So we now want to study this in a region where this omega r star, where we are in a frequency domain, where this omega r star is much smaller than 1. So this is the region where the mapping takes place. And it turns out that from this solution, once we try to expand it, for small values of omega r star, this phi1 in is precisely this number, and they match Bannon. So they are quite consistent. So the lesson is that what we were seeing, the logarithmic behavior, that's not to be taken literally valid all the way until here, because that equation we are solving, only the validity of that differential equation is only the exterior. But in the interior, so this answer is still valid near here, but if we want to carry it inward, we have better taken into account this non-trivial isometry that's at play, and in the end, they match perfect. So we get something nice and
It was inconsistent. Look at this truncation.
indeed, yeah, but I don't think that the person is so I think but indeed, I mean, we can always try to find an inconsistency whenever you solve this differential equation by looking at order of magnitude, or not order of magnitude, but looking at the scaling now with respect to the radial form. And for example, I mean, one of the ways that I first found inconsistency was, assuming some solution like r minus r, let's say some power delta, and then find that okay, it's not squaring up. I mean, you need this extra term in the whole story. So I mean, under, for example, this scaling, this term and this term, they are equally important. Yeah, so this is actually, but since we are dealing with unusual fluid dynamics, we have to find something really unusual. And what unusual thing do we find? So this was that the whole discussion so far was at order epsilon. And this coefficient A determines obviously the as we can see from here, the sort of normalizable component of the scalar field, and therefore the expectation value of the dual scalar operator is CF. And this A in this particular case turns out to be order omega. It's proportional to omega. So in conventional fluid dynamics, any polynomial in omega or k, they are fine, because when we take their Fourier transform, they correspond to delta function or derivatives of delta function. Therefore, the relations are local. But there's something really unusual about this fluid dynamics. That okay, you will say that okay, this was about first order, how do you know that second and higher order are simply defined? So okay, we can do that too. And so how much time do I have? 10 minutes, right? Okay, okay. So I don't think I'll go much further today, but I think it was important to emphasize the key aspects of the physics. Now, what happens is that second and higher orders in the expectation value, for example, there will be some, let's say you want to, at second order, the expectation value of the given scalar operator that goes like omega square log omega over mu. And this is sort of the real interesting part of the story, that because of this reason, there's a new non-analyticity in the Fourier space. So when translated into real space, when you take a Fourier transform, this does not lead to just delta function, it's the delta p minus p prime. What this leads is to some non-trivial kernel of p minus p prime, which means that this so when obviously when we try to write the expression as the operators, we practice some constitutive relations of the fluid, but this constitutive relation becomes non-local in time and only in this special time coordinate because of this near horizon enhancement of symmetry and at second and high order, this non-locality persists. But they do not become non-local in space because even here, I mean, there can be some log in generic high order, there can be some order k square or whatever. But this spatial components, the spatial components of the momentum, they are, it turns out that they always appear as polynomials. So one of the lessons is that in this new regime of fluid dynamics, we always have some non-localities because of this emergent symmetry associated with ADS. And so I also, but after okay, that's a great one. The expansion as we understand it, I mean, in the usual case, that obviously is modified here. But in spite of this non-locality, there exists a well-defined perturbative expansion because it's the perturbative, in the perturbative expansion, what happens is this. So this epsilon is order omega over mu or p over mu, but we get something like at, let's say, order epsilon to the n, something like log of omega over m to the n minus 1. Although this is non-analytic, but at higher and higher order to n, each of the terms are smaller. So as a sensible perturbative expansion, this poses no problem as far as we can see. But there's a, I mean, it's not strictly speaking fluid dynamics because fluid, I mean, what we understand is fluid dynamics is in the opposite, but omega or t are really much smaller than p or v. So this is this is what we call some unconventional fluid dynamics, and we also worked out what happens when we take into account in this new regime finite temperature corrections. And in a finite temperature case, what happens is that you get another new perturbative parameter in terms of p over omega. So there are new sources of non-locality at play, because in general, say at order epsilon n, you can have arbitrary powers of p over omega. There can be arbitrary powers of omega in the denominator, which would again give rise to some similar non-locality that I had discussed. But again, the perturbative expansion is under control because this p over omega is taken to be much smaller than 1 in the particular regime that we are interested in. And there are also some non-perturbative corrections, which I don't go into now. And
So this is a very cold fluid,
yes,
very close to this, presumably vacuum state, with high chemical pressure.
right.
Is there a way to organize tension and that?
Oh, in terms of even in terms of some Lagrangian like that's not immediately obvious to me, but I think people have been working on this, trying to write distributive mechanics in terms of some Lagrangian description in some auxiliary systems and so on.
What's weird is you're just saying there's something universal about it.
Yeah,
And
indeed.
there's no reason for it to be universal.
Yeah, but the universality, because of very low temperature and gravitational dual that develop some. Okay, at least in universality, in the sense that it applies when it applies in the sense that whenever there's some ADS to emergent isometric emergent or ADS to fixed point in the RG flow, that we can give rise to such interesting such features.
Yeah, it seems counterintuitive.
Yeah, indeed. Yeah, and it was to me or I mean or to us when we first discussed this stuff. But like, sorry.
What would it call that? Those temperatures should be very specific. So you know about all the details. You wouldn't have universal. Any
Hydrodynamic plus radius 2.
Yeah.
Yeah.
Yeah, so that's the other one. Like if you do this, how do you know that it has universal? What kind of
Zero
Yeah.
very
Yeah. For example, in recent years, for example, like
no differential. Yeah, very special. That's the generic.
yeah. For example, just from the gravitational side, whenever we have some ADS to the low energy dynamics, and I don't have maybe time to go into their is universally described by the JT model, which is for example, will be the low energy sector of S by K, and whenever there's some Schwarzschild like degree of freedom in the low energy theory, this would be universal.
Some almost global model.
Exactly. Exactly. Yeah. So and obviously we had discussed much more, and one of the things that I think I probably will not have much time to discuss the strong cosmic synthesis story that I also had, but one interesting thing about the story is that the regime of fluid dynamics in some sense it's rather unstable. This is that if we start with some fluid configuration at low temperature, let's say in this regime, and we allow for Cauchy evolution of this data using the Navier-Stokes equation, it turns out that the fluid heats up very quickly and it goes out of this regime in a rather quick way. For example, at a let's say if the generic time scale is, let's say, order t, let's say delta t, the ticking time scale when the cold fluid heats up in is ordinary. And in case of this unconventional fluid dynamics, and analysis, I mean, I could carry out the analysis, but this time scale is actually much shortened by this factor. So this T over omega was, oh sorry, so it's the wrong way. So this time scale is now much shortened because of this. If you try to follow the evolution of the fluid, I mean, just as an initial value problem. And okay, another interesting thing is that the non-localities that I mentioned, they appear only at order epsilon square or higher. In particular, at order epsilon, the constitutive relations, let's say T mu nu 1, and I can write J mu 1, they are completely local. And from these constitutive relations, obviously we can try to find the analogous of the hydrodynamic mode, which have some characteristics of personal relations. And because of someone in the audience, I will say that it turns out that in this particular case, in this region of fluid dynamics, theta over x is exactly equal to 1 over 4 pi. So this is and already we did a lot more in story. For example, you could also try and discuss, for example, what happens when you because the entire frequency dependence is responsible for this non-locality. What happens when you have let's say just spatially dependent locality, just momentum runner, but just completely stationary configuration. In that case, it turns out that you can have some attractor mechanism. Now the boundary fluids will have some electric or magnetic fields turned on, or they will be in some non-trivial gravitational background because some non-normalizable mode of the metric and gauge field will be turned on, which will so this is just part of, so this toy model actually motivates sort of all the interrelated story that we had, and interesting new physics that comes from the ADS2 region about this fluid dynamics. So I guess I probably won't have much time to go into my cosmic synthesis story, but I would just like to probably describe it in words what happens. So what happens there is also it was known from some recent works which involves in for example the Lisbon group. They found that in some cases, for example, RNDS or ADS3, this has under neutral or charge perturbations for near-extremal black holes. There was a violation of the strong cosmic censorship conjecture, and to those were uninitiated, the strong cosmic censorship conjecture implies that the inner horizon, if present, must be generically unstable, otherwise GR breaks down as a predictive field. Because let's say we have some Minkowski space-time. So this Gaussian horizon is the maximum extent to which you can evolve given some initial data. But in recent times, in case of this particular geometries, people found violations of the strong cosmic censorship conjecture, namely that under generic perturbations, the perturbations seem to remain finite here. And for example, people take some scalar field phi, scalar field behaves as CK near the cosmic horizon, where I mean roughly it becomes k times differentiable, and if it becomes sufficiently differentiable, then there's no problem because the resulting back reaction is not that much and remains smooth. So one interesting aspect of this black hole that they were all nearly extremal, and this sort of went unnoticed in the literature that they had this feature in common, and this is why I mean, motivated by my studies of ABS2, I was tempted to explore whether this near-extremality had anything to do with the strong cosmic censorship conjecture, and I found that for for some sufficiently some compact initial and boundary data for the ABS2 black hole, so I was studying the scalar field. This was the sort of most striking result that, and the strongest result so far, that it becomes infinity, that it becomes infinitely differentiable. No matter how many derivatives you act on the scalar field with, it always remains smooth and finite on the cosmic horizon, and the resulting back reaction, you can see that it remains finite. And obviously, so this infinity result I found for scalar field in this okay, in the first paper of mine, but during my PhD thesis, I happened to generalize it for charge perturbation for charge ABS2 black holes, and this was interesting because charge perturbation for charge ABS2 black hole could also be generalized to rotating black holes in higher dimensions or rotating globes. So this was sort of a story which I unfortunately don't have any more time to discuss, but I would be happy to answer any question about it or anything else. So thank you very much.
Yeah, so what did you have to say exactly about the strong cognitive sensitivity as it pertains to the dimensionality?
Oh, no, it doesn't. So my motivation was to discuss two different aspects today, but it took up most of the time. So anyway, I'm not unhappy about it. So anyway, so I just wanted to show that the ADS2 region is responsible for many interesting features. So the main outcome of this strong cosmic censorship, the result that I found is that it's the ADS2 region that's responsible for violation if it's present at all. But obviously, the fact that you have some ADS2 geometry anytime in the picture doesn't mean that those strong cosmic censorship will be generically violated. For example, for asymptotically flat black holes, it's known that, for example, again, by the work of Chandrasekhar here, it was known that the perturbations are generically they blow up in a because Chandrasekhar will part in that. And so, what my work does is that it explains why it is present, if it is present. I mean, it doesn't say that whenever you have, I mean, I'm not making an universal statement that whenever you have an ADS, you will have violations of strong cosmic censorship, because it's also very important to take into account the asymptotics of your space time. So for example, in ADS and in flat, in high enough dimensions, I mean, they are known not to violate strong cosmic censorship. It's pretty robust, but Disitter, for example, has exhibited some violations, and so this work applies to that because even in case of Disitter, you get some near horizon ADS2 region for design.
Now, there was a paper by quantum background.
Yeah, there has been some discussion on that, but yes, indeed. Yeah. So what my particular scenario is just pure ABS2. I have to look at this paper that you mentioned, but in most cases of 2D gravity, which people consider, people don't usually have this exact ABS2, which is sort of much more symmetrical than other, just generally 2D spaces. I think what people usually do, if I'm not mistaken, I mean, they usually just truncate this part of the metric and take the 2D subsector and forget about sphere or compact direction. But it would be nice, and there have been some items that even in terms of ADS3, which does show a violation, some higher order quantum back reaction might reinforce cosmic censorship, but I would love to know more about that.
All right, just to say what I'm so we have this regime that's the initial regime where omega and k are way smaller than TU.
Right.
And
So in this case, so this is what I'm saying. So in this particular case, what I did was Q was exactly equal to 0 just for illustration. But they are much smaller than mu to define some sensible expansion. Because if you have some very high omega or you cannot really control the equal.
either the standard regime before Aristotle.
Yeah.
Because we can connect this gravity theory with some fluid dynamics and have an Aristotle.
Exactly.
You're going to have a very well-defined fluid dynamics framework.
Yeah.
On which has all local functions and all.
Right.
So therefore, the regime you're finding is no local.
Right.
So do you have some kind of description of this theory that gives it some local, like some kind of noisy Navier stokes?
Not yet. That would be interesting to explore. But yeah.
Like you really have, you can calculate simple layers, you see that they are non-local.
Right.
Say, okay, this theory is there.
Yeah. I mean, it's
kind of
yeah. Yeah, I mean, we are doing it at the level of some effective theory, and whatever gravity is telling us, we need to just taking that serious. Yeah, but and some more sort of micro or metaphysical theory we have to think about.
You said that some people try to work on effects of actions that describe the regime.
No. Yeah, I will have to yeah.
On this regime, like, okay, so we're talking about some kind of fluid dynamics, right?
Yeah. Yeah. So you are right to put it in here.
Yeah, but it was kind of my question: how much the fluid dynamics structure?
Yeah, so that's a great. So it does have some character. So up to first order in the expansion, as I said, I mean, it does show something like the dissipative behavior. For example, up to first order this T. Okay, so this T mu this exactly has this ideal fluid minus 2 eta sigma mu, where the sigma mu is eta plus it's that eta is that famous value, and this J has some again ideal mu minus some dissipative term. So there's some certainty here which some would say is going to be happening. So up to this first order, everything is local. And okay, there's one more certainty in case of charge fluid. There's also the charge diffusion mode, which is the dissipative mode. For example, generally just on the space density, you get a pair of sound modes. I mean, when you don't have to charge it, and one this shear mode, which this was the sound. So sound mode has a real part, which gives you this speed of sound, so to say, and which is completely determined by, for example, the conformal nature of the boundary theory. But in case of this J, you have another charge diffusion mode. And for that charge diffusion mode, it turns out that you need take into account the certainty that this charge diffusion mode actually mixes with all these non-local modes. So even though you want to this the charge diffusion mode is associated with some local constitutive relation, it turns out that at the same order, all the high order non-localities come into play. But it so happens that you get lucky that for this spatial trajectory of charge diffusion mode in space of perturbation, that is completely local, and which is something nice. But here we had some discussion with some of the people, and it's essentially guaranteed by the first law of thermodynamics that the charge diffusion mode will have. Okay. And so that when we first were finding the dispersion relation, we had some anomaly of a coefficient for the charge diffusion mode with respect to the conventional fluid dynamics. But because of the first law of thermodynamics, you can argue that the charge diffusion mode will have the exact same relation as in conventional fluid dynamics. But then the trouble is that the charge diffusion mode, the modes that are responsible for it, they appear at same order where the non-local effects get important. But it turns out that you can switch up all the non-local modes, and there's a very sort of spatial measured zero trajectory in the space of perturbation, in which the constitutive relations are still linear, even if it's a higher order in perturbation. Yeah, sorry, that's probably way to jump in, but I may have to explain.
Thank you, speaker again.